So before going to start today's talk, today's session by Dr. Santanu Jana on colloidal quantum dots, a building block of nanoscience and technology, I'd like to give a small brief introduction about Dr. Jana. Dr. Santanu Jana did his bachelor's and master's from the Premier University of India, that is University of Calcutta, Kolkata. He obtained his PhD from the same oldest university in the India and worked at an Indian Association for the Cultivation of Sciences, Kolkata, on the topics of doping of quantum dots. Prior to work as postdoctoral fellow in Paris, France, for 4 years, he was also served for Singapore Bioengineering Consortium, Agency for Science and Technology and Research, Singapore, for an year. At present, Dr. Jana, working as an auxiliary researcher, is a very prestigious post in the FCT at CINMAT University of Lisbon, Portugal. Dr. Jana received several awards or fellowships in his short career. Some of them are prestigious Marie Sklodowska-Curie Individual Fellowship in 2015 for the postdoctoral research from European Research Council in Horizon 2020. CNRS Postdoctoral Research Association to work as France Best Poster Award from the Optical Materials International Conference of Young Researchers on Advanced Material Research Society, Singapore, Young Scientist Award from the Material Research Society of India, Kolkata chapter, and many more. He has a number of very good, very excellent publications in prestigious high-impact journals, which includes Nature Electronics, Science Advances, ACS Nano, Angiochem, and many more. With this very short introduction, I'd like to invite Dr. Santanu to take the charge of this session and share his valuable findings and thoughts to our participants. Please, Dr. Jana, please take the session.
Thank you so much, Dr. Panda, to invite me to present mainly my research works and also some basic topic of my research work, which I worked on mainly the quantum dots in last 8-9 years. So basically, quantum dots it can be made from any of the compounds because why it's called dots, because it's like a small dot, means like if you have a pen and you can make a dot on the paper, it looks like same in the paper when you take a printout of the structure of these materials. So the basic title of my talk is Colloidal Quantum Dots, a building block of nanoscience and technology. So I have three days session. So I divided my I divided my 3 sessions in 3 different topic based on quantum dots. First, I will tell about I'll basically tell about what is quantum dot, how we made, what belongs to, and what type of quantum dot, and how we distinguish these are quantum dots or not. So very basic characterizations, different optical properties, and then tomorrow and after tomorrow I'll talk about different fabrication of the device, how we fabricate and how the other people also fabricates the quantum dot device, and then phases of the problems and how could we have a solution to make them a good film. And then last day I like to talk about mainly the different applications of the quantum dots. As it is mostly based on chemistry, today I will talk about mostly based on chemistry, and next day few are engineering based and also the chemistry and physics part. So as it's a last talk, and if people are listening from the morning, so I will not take so much time to, and I'm trying to do as easy as possible. So now, what is quantum dots? First question is why we call quantum dots. So you can see it's a small crystal, very small crystal. It could be generally the quantum dots is below 10 nanometers. It should be nanometer scales. You see that it's crystalline image, and you can see it's a very small crystals, and things are there. Very unusual property. Unusual property means suppose one of the bulk crystals, it gives a red color of emission, or red color. It looks like red color, but same material, when it goes to the very nano regime, like very small, means what you cannot see your naked eye. So that can give a different color. Maybe their mobility, their electron flow, everything completely changes from their bulk counterpart. So that's why it has a very unusual property, and it is quite nowadays quite established and already in electronics. And maybe you can find some quantum dot LED TV in the supermarket. It's a big LED TV. So Samsung already made the quantum dot TV from the colloidal quantum dot solution. So basically it's why, but we need to understand why we call it quantum dots. First, as I say, these are very small particle, mainly from the semiconductors. Like it should be have a band gap, like it could have a one valence band and one conduction bands, and it should have a semiconductor. But metals, semi-metals, and other things we can make, but not so easy. Means in general point of view, the quantum dots are made from semiconductors, and the typical dimension is 1 to 10 nanometer. Means why I am says typical dimensions, because uh, different semiconductor has a different band gap. Like for example, if you take the cadmium selenides, the bulk band gap is around belongs to red part of your visible spectrum. So the maximum size you can go to a 7 to 8 nanometer. But if you go to the lead sulfide or lead selenides, it's some mid of IR. The band gap is present in the mid of IR. So mid of IR means your particle size goes to maximum 12 or 13, 14 nanometer. So that's why I say the typical dimension means maximum number of maximum quantum dots, which belongs to range 1 to 10 nanometer. And now why it's quantum dots? Because it has some quantum mechanical view, means quantum confinement effect. That's why we call the dots looks like dot, and it behaves like a it has a quantum mechanics. It have a quantum mechanics inside. You can see, and it behaves like simple atom. If you look the atom in the left corner of the slides, it has a nucleus has a proton and neutron, and then electron are surrounding them. Similarly, quantum dot has a core, like a core, and its a core is a confinement, fully confinement, and electrons are is when electrons are moving around the core. So that's why, because the electrons are confinement in the box kind of things. So that's why sometimes these quantum dots called the artificial atom. And you can see there is mainly based properties. The absorbance it absorbs in broad range of spectrum, like a in the same particle you can get from the blue, you can get from the red, you can get yellow, whatever you like, you can get the this color of emissions. And you can see the length scale here. The animal cell, it's 100 micrometer, and atom is 1 angstrom, close to 1 angstrom. So, and our quantum dots belongs to this area, 1 nanometer, 1 to 10 nanometers. So that's why you can it's very good processable, means you can take it in solution. Nowadays people also use the biological application, different biological application. So now, so why we call quantum dots? Uh, because if you see the dot here, it's suppose it's a bulk nanocrystals, sorry, bulk semiconductor. There is no confinement, and if you see the your band structure, it's a completely there is no discrete energy, means it's overlaps from one band to another. one band to another. So that's why it's a bulk, and it's called 3D nanocrystals. Means bulk means, suppose the now question is, we call this nanocrystal because it has a crystalline structure. Basically, all the quantum dots has a crystalline structures, because any you can make the amorphous nanoparticle in this region. Like you can make a amorphous nanoparticle within 1 to 10 nanometer, but you cannot get the confinement, because when it goes the amorphous, there is a different trap. You cannot change the trap state in the amorphous crystal. So that's why you have to be crystalline, and when it's crystalline, the atoms are organized very well. So that's why it needs to be crystalline. So when it goes to 3D to one dimensional, you see this is a one dimensional confinement, means electrons only flow along along other two directions. So in these directions, electron cannot flow. So that's why it's called the quantum well, means electrons is in the well, they cannot jump here and there. And then again, you see, it can be platelet, and in physics it's generally squeezed in between two large band gap material. But here, if you see the quantum rod, its confinement means it has a 2D confinement, means it's two-dimensional, means electron cannot move two direction, x or y direction, so it only move in the z direction. So it's called the quantum rod. And then when it comes to quantum dots, we say scientists say it's a zero dimension. Why zero dimension? Because electrons cannot move any three directions. In all direction it confinement. So that's why it's a zero dimensional material. So it's completely confined, and you can see the energy level. It's completely discrete. Means you can distinguish the valence band and interband structure. So and it's moves from the bulk band gap. And when you get the size, when you make the size changes, the confinement changes. So you will have a different gap of the particle. So that's why you will see the different emission. I will tell you more details here. Look at the left side. It's a bulk band gap. So it's a bulk semiconductor, like it's a big box, and you are shining a light. That means you are giving energy. So electrons are in the valence band, and electron goes to valence band to the conduction band, and it's emits. As it's a bulk band gap, it emits it's a above the, if it's a emitting material, it can emit very small, very slight emission, but it's not a very good. But when you go to the confinement structure, like you can see, when you go to the small size, you can see its energy level are getting discrete, because overlap between the orbital is very strong. So you will have a separate energy level, and when electron goes from the valence band to the conduction band, when it goes to the valence band to the conduction band, so you have a discrete energy. So electron can go from here to a top level, and then when it emits, it gives the energy, and you can see the gap between two level getting increases. It's a small particle, so that's why gap is higher. It's behave like a particle in box in quantum mechanics. Means depends on inversely proportional on the length of the box. That means if you have a larger box, your energy level is lower. That means you are getting the red part of the spectrum. So when you have a smaller box, your means length is small, so it will be the smaller box. So you will have you have a larger box, so smaller box, you will have a higher emissions. You can see here it's just opposite of the inversely proportional to the length, and you can see when particle size increases, the band gap decreases, and you can get from the red part spectrum to the blue part spectrum. And interestingly, suppose, for example, take an example of the cadmium selenides. So as a selenide is a full of electron, it generally forms the balancement of the nanocrystals, and the cadmium 2 plus, it generally form the conduction band of the crystals. And you can see as selenium is a full of electron, it does not move very well, but valence band is a empty orbital, so it moves drastically, and the band gap tuning is only for the depends on the conduction band. And in by this tuning you can get a different type of quantum dots. Once why I say type, okay, so if you see the periodic table here, then I will go to the different type of quantum dots. And you cannot make all the nanocrystals from, you can make, there is plenty of nanocrystals in literature, but you cannot get the, from the all material from the all material for the quantum dots. Generally, 2,6 chalcogenide like a cadmium selenides, cadmium sulfides, zinc sulfide, zinc selenide. So zinc 2 here and 6 here. So these two can form a good semiconductor, which can, where we can see the very nice emissions and different properties, and other optical properties also, electronic properties also, and also the 3,5 mainly phosphide. Also people are doing arsenides, because but problem is the arsenide is a toxic, so mostly toxic, so that's why they don't use. But generally indium phosphides and indium arsenate, etc. Also like a 4,6 material, like a people use the, people don't use the tin, because tin has a different oxidation number, like a +2 +4, it can goes very fast in the air. So people only use the lead. So lead sulfide, lead selenide, lead tellurides. So and these are very, though is a toxic, but these are very good material for the thermal imaging and other things, because it's emits in NIR emission. And nowadays mostly people works on the metal halide peroxides or organic inorganic halide peroxides, and generally people choose the metal as a lead, tin, and nowadays indium, it's a double perovskites and other things. And halides, they choose the, generally choose the iodine and bromine, also fewer chlorine, because chlorine is a very small size. That's why nowadays it's not very good for different applications. That's why chlorine is not famous for the perovskites nanocrystals. Sure. Now uh, how do we synthesize? Generally, these are two different way we can make the so we can make the quantum dots, like a top-down technique. Means it's very simple. Like if you have a big rock and then you cut the rock in different shape, like here. So generally like a lithography or different deposition or etching, means you are etching a surface of the crystals, big crystals, so you can have a small crystals. And other thing is bottom up technique, means maybe the chemical, maybe cell per cell, means like here you have a small wood and small nails, and you can make a big home. Similarly here, if you have a compound, different compound of the chemical compound of the materials, and you are making the dots, and you are controlling the your crystal size and everything. So, and here is the mostly people do the colloidal synthesis, because you can have a large quantity of the dots material. But for the physics point of view, means if you want to study some literature related work, so now people make the through using the lithography. But for the application purpose, it's the mostly people mostly use the colloidal synthesis. And if you see the colloidal synthesis, it has a very specific to the chemical synthesis. It has a magnetic stirrer, and we have a 3-neck flask. So there is some solution, and generally we do the high temperature solution technique, and we have a temperature sensor, and we use the inert atmosphere, and we use the nitrogen flow, And you can inject the precursor. So you have a rubber cock here, so you can inject different precursor whenever you like, and you can control the different size of the nanocrystals. Nanocrystals, and if you see as it's a solution, you can stop anytime. You can control from the outside, so you can stop immediately. You can, if you want to cool down slowly, you can cool down slowly. So whatever you like, you have a control on your synthesis. So this is the good invention of the synthesis of the quantum dot, though it's completely nowadays very stabilized, and already there is some robotic arms in the industry, so they control the synthesis. And basically, as I told in earlier, these are very tiny crystals, and in synthesis we use some ligands. Ligands means some amines or thiols or different acid means not a hydrochloric acid. It's a fatty acid like stearic acid, oleic acid. So you have a some polar group here, and you have a very long tail of the carbon chain. So these nanocrystal generally, that's why it's dispersed in the solvent like non-polar solvent like hexane, toluene, chloroform, uh, these things. Also, of course, you can transfer to the water or polar solvent by changing the ligand, and people already use this for the biological application. And I think this is one small video. You can see how we can make the quantum dots. Um, and you see, we take an injection, and it's a 3-neck flask, and you can see it forms a brown color. You see the color changes from time to time, and it's looks like black, but it's dark red. It's a dilute solution of the precursor on nanocrystals. Now you see under UV light, it shows blue, green, yellow, blue. This you can see, and also you can see the red, orange in the same pot of reaction. So this is the main best part of these quantum dots. Only one single reaction you can have a fully behavior colors, means from the violet to red color you can control, and you see the particles. These are the nanocrystals. It's
Santanu,
yes. Hello, hello. Can you hear me?
Santanu, is audible to you?
Yes, yes, no, yeah. But few minutes ago,
Yeah, I
yeah.
think
Now it's fine.
okay, it's okay. Can you please repeat the video once again, because sometimes it's not visible to clearly that time because network
Okay.
issues. So please repeat the video.
Oh, okay. Sure.
Thank you.
Okay. So you see, we take a solution in injections, and it's a thin flask. We inject very fast in high temperature. You see, you can see it's a color getting changes, and you can see now it's completely dark, but it's showing the red emissions here. And you can see under UV light, it's very bright emissions, very dilute solutions, and you can see the red color emissions also. You can see this is the best synthesis technique. So you can have a all particle you can have a all different emissions from the single materials. Means only one synthesis technique, you can have a from blue emissions to the complete red emissions. And you can see these are the only one example of the size of the particles. It's around 7 nanometer, and it's homogeneously dispersed, and there is, you can see, all the particles looks like same, though very small. There are smaller small particles or triangular, but these are very less. All particle look same, and it's very crystalline. And you can look at that, these are highly crystalline, and you can see the atoms in the crystals. It's nanometer scale, 5 nanometer, and you can see when it's very crystalline, you can see the atomic level of the crystal. And these are different kind of plane. So this is the how we make the quantum dots, and this is the general synthesis of the quantum dots. So you can make the different rods, different tetrapods, different structure. And you see, as I told before that, did they have a different absorbance? Because when you go to the blue then red, you can see it's tuning from the blue part of the spectrum to the red part of the spectrum, and it can absorb all the visible window. And these are the different size of the nanocrystals, like 1.7 nanometer to the almost 15 nanometer. And so these are all from the same nanoparticles. And you see that this is the one absorbance spectra. It does not look like a when you measure the dye, you don't have a continuous spectrum like this. It has a go down, but here, as it's a semiconductors and it's a continuous band, and you can distinguish the different interband transition from the absorbance. Just for example, here different step of the interband transitions, and you can see these are the different transitions just you can get from the absorbance. So when this kind of absorbance you get, that means your particle size, your particle is highly distributed and very good crystalline. That's why you are getting um, high quality absorbance. So this is the first characterizations of the your quantum dots, to get the to understand your from your synthesis the quality of the nanocrystals. So, and next is the emissions. And you can see this is the emission spectrum, photon emission spectrum from from the whole visible window it covers. And you can see the different emissions, and all the fluid half maxima of the spectrum is highly distributed. That suggests your particle also good distributed. So these two methods, like absorbance and emissions, are main tool to understand the quantum dot behavior of the quantum dots. It's a dots, or it's a tetrapod, or it's a quantum well. So you can distinguish very well. Then you will go to the other characterization like a TEM, SEM, XRT. But before that, you have to do first the absorbance and emission, so you can understand how your particle distribution is. And this is the image of the very bright nanocrystal dispersed in the solution. And as I told, you see the band gap increases, and particle band gap increases, but so particle size decreases. And you can see when particle size smaller, band gap is higher, so you will have a violet emission. And particles here, particle size is bigger, band gap is smaller, so you will have a red color emissions of the solutions. So, and now, as I told, we have a different type of quantum dots. Like this is type 1. That means we have a different kind of quantum dots. This means we have a core and cell. You can get a cell from the different semiconductors. So you can make a cell like which have a higher band gap from the core, like these are core. So it's, if you took the cadmium selenides and zinc sulfide cell, so it's a type 1. Man, that means in type 1, in center part means core is a smaller band gap material, and cell is a higher band gap material. Like here, you can see the band gap is very high and small. So it's a type 1, means your electron and hole, it's confinement only core. Now it is reverse type 1. That means you have a inner material, core material is a higher band gap, and shell material is a smaller band gap. So you can make a quantum oil by using the reverse type 1. That means you have a zinc sulfide here, cadmium selenides there, and you can cover another zinc sulfide. So you will have a squeeze of the exciton, means your electron is in the oil. So that's why you can get the quantum oil structure, quantum oil structure from the reverse type 1. And then other is type 2. Type 2 means your band is not covering each other, so it can align anywhere of the cell material. Like here you can see it's a cell, cadmium selenides, and it's a zinc telluride cell. It's a core cadmium selenide, it's a zinc telluride cell. So the band gap is not aligning each other, so it can be up, it can be down. And when electron exciton transfer, when if you shine the light, so electron hole generated here, so electron combines through here to here, means you will have a, you are shining here, but you will get a emission from the different structure. So these are type 2. Basically people are using the type 1 material because it is stabilized, it is stable, but other are not so much stable. And so initially people are interested on that, but after that, as it is a synthesis, is very hard. So people are not continuing this type of work after that, after a few years. And this is a one example of, one example of quantum rods, like a CDSE rod. Means you have a rod and you have a ligand binding on the different surface, and you can see the small rod, maybe it's very tiny to look to see, but these are very small rod, one dimensional rod. And these are, you can see, long. So when you increase the diameter of the rod, because in the other part, means the long part of the rod, it's already beyond to band gap, means it's more than 10 nanometer or 20 nanometer, close to 20 nanometer. So only you can change the along the one direction, means like a z direction, means this diameter of the rod. So you can change the diameter of the rod, means you will have a only band gap belongs to, depends on the diameter of the rod, means electron flow is in two directions. So that's why you can get the emission from tuning emissions from the different size of rod. These are very good material when you make a rod, because then electron can flow on the single crystals in one direction to the another direction. And I will tell about in tomorrow or day after tomorrow about why the other means electrons, means mobility and other things are higher in the rods. And there is another structure, is a tetrapod. Tetrapod means you have a head here and you have a four leg, means 1 2 3 4. Here you can see from the, so inside these are the two different crystal structure. Like inside means head part, the inside part, these are starting from the cubic structure, like cadmium selenide, cadmium telluride, zinc telluride, whatever you need. Here you can see the TM images, the small dots, it are the head, and it has a four leg. You can see the three leg in TM because it's a two-dimensional image, but your particle is three-dimensional. So one pot you cannot see in the TM because it's in above of the your head. So here you can see the structure. These are the head part inside. So, and is a cubic structure, and from the four faces it grow as a wood-shaped phase. So you can see the four part, and from this you can get also different emissions and different electronic properties. And it is interesting because of you have a two different crystal structure in one systems, like you have a jinglet systems and you have a wood-shaped systems in the single structure. So that's why you will have a different electronic properties and optical properties from that tetrapod. So now this is another things. It's a platelet. It's called the quantum well. It's a very thin. Thin means around 1.5 nanometer, 1.9 nanometer, depends on how thick is it. Here it is, you can see 1.5 nanometer. That means 1 2 3 4 5 6, and and these are only selenites, and these are cadmium. Means this belongs to 5.5 monolayer. Half monolayer means one cadmium, one selenites. Here you can see one layer, two, three, four, five. So 5.5 means 5 monolayer of the only 5 monolayers. So you can distinguish the platelet with the confinements, and exciton. And you can see exciton only electron only flow in the one direction, other two directions electron flow other two directions, and its confinement along strongly along the one dimension, means because it cannot move in the this direction. So that's why it behaves like a quantum well in single systems, but it behaves like a quantum well. And as I told you, thickness can be controlled by the half of lattice parameter, like a 0.31, like a half of one monolayer. And interestingly, in solution technique, you can change the thickness of the quantum well, and you can see we can synthesize from the 2 monolayer, 3, 4, and 5 monolayer, and nowadays also 7, 8 monolayer we can change. And interestingly, there is no mixture of the platelets, means 4 and 3 monolayer. This is the beauty of the chemical synthesis. So when you do the synthesis, chemical synthesis, you will, if you control your synthesis by temperature, by ligand, by solution, you will have only the single type of platelet. And one thing, it has a higher optical behavior, optical properties than the quantum dots, at almost 10 times higher. So that's why it's called the next generations of the quantum dots, though it is not dot, but we say it because it's a platelet kind of structure, but it's very small, around 15 nanometer length. Also, we can change the these two length. It can be rectangular shape, it can be square shape, and it is a good things. Look at the here, it's a 3 4 monolayer and it's a 5 monolayer. You can see distinguished, very highly distinguished from 4 to 5 monolayer absorbance and emission. And the emission spectrum is very sharp, means it's fall in the visible region, but its fluid half maxima is very low, it's close to thermal temperature. So that's why you can use this material for the lasing and for other detection related properties. And these are the also different size of platelets and different thickness of platelet, and you will have a bright emissions, and you can see we can make some platelet type of structure, but it's embedded in the polymer, so you can use in the as a light emitting diodes for application of purpose. And these are the TM images of the platelets. You can see it's a very highly dispersed and a square shape, square, rectangle, and also we can round shape platelets. And these are just controlled by the chemical process. So now I will go to the another part of another type of quantum dots. So why recently people do. So it's called doping. So only too far till now, I only told about the only single type of quantum dots, means it has only one material, like a cadmium selenides, means we have a cadmium and we have a selenium. Now I like to dope in quantum dots. It's not like interstitial doping. It's not like you can have a extra atom inside the crystals. It's not like that. It's not like a doping in silicon. It's like you are replacing one cadmium atom inside the crystals. And suppose this is a foreign ion, like if you say the manganese, copper mostly used, and if you dope it, it just replaced one of the atom of the host nanocrystals. That means here, let's say it's a cadmium selenides, and it removes the one of the cadmium ion from there, and at the end, it creates a defect. Sometimes it creates a defect, sometimes it creates its own band level inside the valence band and conduction band. So you will have a different emissions from the same nanocrystals. So by using the doping. And also if you see the manganese, it creates the two level here exciton energy transfer from the host to manganese, and it can have a orange emissions from there. And this is the final output of the synthesis. It's in a 3-neck flask. You see, it's a zinc selenides. It gives very blue emissions. You dope the manganese, and the doping percentage is almost close to 1% or less than this. You will see very bright yellow emissions. And if you put the copper, it gives the very green emissions. And again, if you put a manganese with a little bit of sulfur, it can have a red color of emissions. And another things, if you put the copper in other nanocrystals like cadmium zinc selenide, you will have a full visible window. And here you can see, because it's little bit low toxic, because cadmium concentration decreases, you will have a not fully cadmium sulfides, and also quantum will be high. And interesting thing is that without coating, without core cell structure, it is a very stable, it's a very thermally stable in the solution. And these are the things also you can dope with the other transition metal ion, chromium, nickel, copper, and silver also. And you can see it can give a different band level on your structure, and you will have a different emissions from the silver, chromium, nickel, and copper. You can have a different emissions from there. And because it creates a different band level inside the valence band and conduction band. So this is this is that you can see that this is copper dope changing selenide structure. And you can see, as I showed you earlier, these are the digital images of the solution, nanocrystal dispersed in the solution. It's very dilute, but it's very bright. And you can see we can distinguish by the absorbance and emissions. You can see absorbance here is close to 400 nanometer, but your emission is very far, like a 700 and 700. So these are the good things, because it are not overlap. So you do not have a reabsorbance in the solution. So that's why people use the doping. And also you can create a different electronic level and electronic structure. Like if you put a higher amount of copper, you could have a p type or you could have a n type, depends on the copper valency in the nanocrystal. So these are also good materials for the electronics applications. And interestingly, in one pot, you can have a different emissions. Like if you took a zinc selenides, you will have a blue. Then put a manganese, you will have a orange. Put a copper, you will have a green. And again put a cadmium, you will have a red. Just in one systems, you will have a different emissions from there. So this is the good things. Whenever you like which emitting material, you can use this kind of materials for the further application purpose. And it's just nothing else. It just changes the band alignment inside the valence band and conduction band. Like here you can see the manganese here. So you will see the orange emissions. When you put a copper goes here. So this manganese level does not work. So that's why it emits the bluish green emissions. Again, you put some cadmium, because it changes the band gap and its lower level come, and you will have a copper emission and it forms a red. So that's the way you can get different kind of emission, just engineering with a band gap. So these are just basic synthesis of the platelets. It's just how we control the nanoparticle precursor. Like here you use the cadmium precursor, we use the selenide precursor, and it forms tiny platelet, then goes along, and you can change. And you will see that these are the solution, how it looks like. And so I do not want to say this self-assembly. Okay, self-assembly I will talk about later. And these are the things, as I told you, we can transfer also water. You can see it's a copper toxin sulfide, it's very high, it's transfer in water. You can image for biologically. And these are some of the other nanocrystals, how we use, and cadmium zinc sulfide, copper indium sulfide, ternary nanocrystals. And so you can have a magnetic properties from here. And as I told, it's very thermally stable. You can see it's a boiling water, and it's very bright emissions. These are different pH level. So you can have a different cell imaging structure from there. and different ternary nanocrystals. You can see copper indium zinc sulfides, and also the doping with the manganese. So you will have a different kind of variety of emissions from there. So these are the all my talk about the synthesis and others. So for now, for today, I think this is enough for the synthesis part and other things. So tomorrow I will talk about a little bit more details about the crystal structure, how we form the film and fabrications, different fabrication process, and then also applications of the different applications of the this kind of quantum dots and other things. So thank you so much for this.
Well, thank you, Santanu. So already I opened the participants. They can unmute yourself and they can ask questions. I know there are past two sessions we didn't get enough time to ask questions. So if there are any questions about this session, please feel free to ask Santanu, Dr. Santanu. He is here. And in the meantime, I'm sharing also feedback link for the whole page as well test link for the this session. Okay, already I opened the. If people can unmute yourself and ask the question to Dr. Santanu.
Hello.
Hello. Yes.
Good afternoon, sir.
Yes. Tell me.
Actually, really, it's a very nice talk and very informative regarding starting from the that quantum dot growth. My query is about as quantum dot is confined from all direction.
Yes.
So that means it is totally confined. So what about the transport? That means in terms of optical properties is very nice.
Yeah.
Excellent optical properties, which is shown by the quantum dot.
Yes.
But I want to know about what about its transport property?
Okay. Transport properties, like as it is, it's a very good questions. Maybe it's a good questions. I like to tell about the next day. But as you ask me, what about transport? Basically, it's transport through hopping. Means like if you make a film and you give a bias like some voltage, extra power. So inside the electron of your quantum dots, they are excited and now they want to go out. So there is no chance to go out. So they just hop, means one crystal to the another crystal, and in that way. So this way they transport the electron. So now to get the good quality of the good results of the nanocrystals electronics, you need to organize them very well. That means electrons should hopping in very organized way. Otherwise, you will have a loose of electron inside the rod somewhere. Suppose you have a tens of quantum dots sitting together and they are randomly, they are not oriented. So you give a bias and one crystal generated an electron and they needs to go another quantum dot, another dots. So if this is not very close enough or not oriented, it can go anywhere. So you will have a lose of your properties. That's why we need to have a very good quality of film. That's why I told you some of the problem and how do we solve the problem of the transport. So maybe I will talk about more details tomorrow, how the electron transfer through the hopping. Basically, it's transfer to hopping.
Thank you, sir.
Okay, welcome.
Thank you.
Any questions? Please feel free to ask the questions. Ramaya, yeah. You wanted to say something?
Yeah. Yes, sir. So it is very interesting session. Actually, I have one doubt. In the nanoplatelets, we have in the absorption spectrum, we have 3 peaks we get, right?
Yeah,
So,
I can show you just a minute.
yes.
Like here, or maybe it's
Yes,
better
like
to
when
see
we
here.
overlap with emission. Yes, this one.
Yeah.
So what
Yeah.
about other these bands which shows?
These three peaks, like in one, like maybe it will be. I can show you. Last platelet is a platelet structure, okay, and maybe it will be more clear when I show it you here, like here, like it's cut. Its material is same like a cadmium selenides, and you will have a like a one, two, three. These three peak are mostly intense because these three band are here. You can see very weak peak because these are not, it's just like tentative, I tentatively designed here, but when it's in platelet, these are very strongly distinguished each other. So that's why you will have a this one, two, and three peak, and basically it has a heavy hole and light hole transitions, like a these are holes. So when it forms the valence band, it forms the heavy hole, and then there is a light hole, and then last transition. So when it's transition from the heavy hole to the electron, you will have a um, here, maybe here. These are the heavy hole electron transition, means the mass of the hole is higher, and these are the light hole electron transition, and these are the another transitions which belongs to like here it's a, you could not see the very well, but here because it's a thicker platelet, so that's why you will have another band is open, so it's a other interband transition. That's why you can see distinguished, very highly distinguished absorbance in the one platelet. Means it's single platelet. It's not a mixture, but you can see the interband transition from the absorbance. So that's why that's why it is a strongly confined band. Means electron only moving along the one directions.
Thank you, sir. Thank you so
Okay,
much.
welcome.
Is there any more questions? I think there are no more questions. Well, so I think okay. Let me see the chat box. Is there anything? Well, if there are no more questions, I think because
sir,
yeah, please, the answer.
sir,
Yes.
sir. Actually, I'm just anxious about to know that you have shown these quantum dots that in the
Yes.
liquid form in this. So actually, typically when we make some material support, we
Yeah.
want to grow quantum dot over a material. So specifically, it is in solid form,
Yes, that's
crystal.
yeah. That's why I told you that with synthesis in a bulk way, you can get it in solid form like lithography, but it cannot help you when you know you if you made for application for the research purpose. Okay, it is okay. You can grow a quantum dots on top of a silicon or like a whatever you like. That's your interest because you want to study. Okay, if you put maybe like germanium quantum dot on top of silicon, how it will behave, but you will get some results and maybe you will publish somewhere. Okay, but that's not help you to community to make a application because uh, for research purpose that is fine, but for the application purpose, you need to have a large amount of materials. Industrial level, if you go to industrial level, you need to have a large amount of materials. So in that way, you need to go to solution process, or this type of way means you can have a very high amount of materials, higher amount of materials, and then you can process for it. Like if you make a big cover of the glass, and which can emit hold the glass, means like a hold the TV screen. So how can we, if you put the instrument and if you put one dot through the whole of the like a 22-inch TV screen, it will be super cost and no one will buy. So you need to have a very cheaper to make a solution process, maybe not solution process, maybe other process, but you have to be cheaper way. So to make the quantum dots, only cheaper way is a solution process. So that's why you will have a lots of amount of material. You can have a make a film, and from that, if you want to take a 1 nanocrystal also, you can take it. You can drop a very dilute solution and you can get a single nanocrystal. People are measuring the single nanocrystal emissions, single nanoparticle emissions. That's why we do the solution process use. So we are not interested in the growing a single quantum dots on top of the other. We are mostly working on the solution process, mainly this region. Like if you do the biological application, you have to inject some particle inside a body of the mouse or somewhere else. So that way, that time you need lots of material. How can we grow on a single quantum dots, and then you will collect all quantum dots from the top of the some material. So that's why these are nowadays quite famous for making synthesis in the colloidal way.
Yeah, it's actually very interesting. Sir, if you give permission, can I ask another question? Actually,
Yes.
I am very actually anxious about to know. Sir, as we do it generally in quantum well, so depending upon the confinement, we also get the discrete energy level.
Yes.
So we can also get finite wavelength when there is a transition from conduction band to valence band.
Yeah.
So in quantum dot also we can achieve this. At a discretized manner, we can get finite any wavelength we want accordingly we design.
Yes.
So basic phenomena is the same, whether it may be a quantum well or it may be a quantum dot.
Yeah, basic phenomena is same. Yes, but question is what?
The question is then same phenomena. Then what is the difference?
Yes, this difference is here. See, quantum wells and quantum dots. Only electron means exciton. Say you can say the exciton. You can say electron, whatever may be. Electron only can move along two directions. It cannot move the other two directions, other directions. Like if you see here quantum wells, if I can zoom it here very well, you can see only electron move these two directions, means x direction and y direction, but z direction it cannot move. It's only confinement. That's why it's called one-dimensional confinement. And here it's complete confinement along three directions. Now, as you said, the band structure, band formation is bit of same, but when its gas goes to the different dimension, like here, the level of the energy level changes according to that. So that's why you will have a different property from the quantum well and quantum dots. Only this is the difference. Like here also, maybe here. Here also form the molecular orbital and the yes, this is the things. Here in the quantum well also forms this kind of structure, this kind of band level, and also this kind of band level for the valence band, conduction band. And also the dots also form the same, but the level of the these valence band and conduction bands are different because of the overlapping of the in the different dimension. Like these are one dimension means two other two directions overlap is different. So that's why you will have a distinguished absorbance and emission from the quantum dots and quantum wells. Do you get my point?
Yes, yes, sir.
Okay.
Thank you, sir.
Okay.
Yeah, thank you very much for this
Okay.
enlightenment, sir.
Well, thank you, Dr. Sahu and Dr. Jana. So, any other questions? I think no more questions are there. Okay, I just like to share one thing. Today, Dr. Jana shared about the chemical part. Tomorrow morning, first session. So there is a physical method, that is maybe electron beam lithography or some other lithography method. How we can make the quantum devices as well as quantum structure. That will be shared by Dr. Portugal Das from Jadavpur University. So please be tuned. And I already shared the feedback link as well as test link in our chat box already. Please fill up these things, and with this we can close today's session as well as today's talk. Tomorrow we will see all of you at 10 o'clock. Thank you all.